Hello, my name is Nicholas Garcia. I'll be providing a very high-level summary of the security paper entitled Secure and Efficient Software-Based Attestation for Industrial Control Devices with ARM Processors. This paper was written with a a grant from various Singaporean government agencies and foundations through it's mostly a project funded by the Singapore government. The problem that this paper addresses is the lack of what the paper uses as a term attestation, but attestation is trying to verify that the device is not a zombie device being controlled or manipulated by somebody else who's infiltrated the memory of the device. I'll read the text in this slide. Industrial control system devices using ARM processors deployed along the power grid are vulnerable because the device's integrity is not being properly tested. And so there's no checksum being deployed to verify that the device is performing the function it was designed for. And the proposed solution proposed by this paper is that the device uses checksums to verify the integrity of the devices. One of the challenges involved with deploying this solution is that checksums must be calculated within 20 milliseconds to meet the feedback loop requirements of power station devices. The paper states that some in the power grid, some phaser calculation devices require a 20 millisecond feedback time. So the paper uses 20 milliseconds as a benchmark time to calculate checksums. Excuse me. And another challenge is that implementing hardware-based checksums on all vulnerable devices is difficult and expensive. As you can see from the picture in the lower right corner, on the power grid, some of these structures involve hundreds or thousands of individual devices. Each one may have an ARM processor, so this would be expensive and difficult to implement. And one of the solutions addressing implementation challenges is a software solution using only a portion of the device's memory as a basis for the checksum. So as you can see in the picture, this is a portion of the memory in a device using an ARM processor, and this is the entire memory set of the device. And the checksum algorithm uses portions of the memory instead of using the full total memory to calculate a checksum to verify that the device hasn't been tampered with by a malicious attacker. As you can see, one of the problems with using this method is the program counter and data pointer can be manipulated with maybe an overflow buffer method or something else. And so the paper tries to address this by by putting the data pointer and program counter in an area that doesn't utilize the MIPS ARM architecture, so it's less likely to be the data pointer and the program counter might be less likely to be manipulated by a malicious attacker. And just to provide a brief description of some of the terms used in this paper, attestation is the process of verifying that a device has not been maliciously tampered with and it's genuine. So in other words, verifying that the device isn't a Trojan horse trying to get access to other devices or performing a malicious function. And root of trust is it's a concept developed to attempt to try to stop malicious attackers from using a device's own resource to attack other devices or perform malicious functions. It's a level of privilege inaccessible to device users, and it's ideally used for attestation. But there's some arguments within, and there's some arguments within the security, industrial control devices security field that root of trust might be used by companies, for example, to ensure that only their products can be used and block other competing companies' programs or hardware. And that's just one example, but there's some arguments about the root of trust, utilizing the root of trust concept. Currently, all U.S. Army computers are required to have a root of trust implemented and installed within their computers. But there's just some arguments within the community, the security community, about that. And a SWORT is a software-only root of trust. A hardware implementation of this, the root of trust, can be difficult because there's so many devices that, for example, the power grid uses, and so replacing all those devices or upgrading them to implement a hardware solution might be more difficult than using software attestation. So this paper proposes using a SWORT root of trust solution for attestation. And the algorithm that this paper proposes is called memory stride. It's a subset of a SWORT, the SWORT type root of trust solution, and that's proposed by the authors of this paper. The SWORT memory stride algorithm proposes that a fixed amount to stride across memory for generating a checksum is calculated using a random number generator. And a lot of the process of this SWORT memory stride algorithm involves creating a nonce or seed to make a random number to decide where to start in memory for the stride, and where to start for the calculating code. But I'll go into that later. The place where it counts code. The checksum calculation is alternated continuously, and the paper uses the term interleaved between the memory of the SWORT code and the memory retrieved in the strides until a checksum is calculated. The strides, the amount of a stride is a number randomly generated by the stride SWORT code. So it basically steps through the code to utilize the checksum algorithm until all of the code other than the SWORT code has been checked through. So the code alternates between using the SWORT code, the actual SWORT code itself as in the checksum algorithm, and using the step through the stride code that it's step through. And again, the paper calls that interleaving. And it's a very general overview of what the SWORT code does in a nutshell. It generates a random number to indicate how much the checksum strides through the code at each step. It computes the checksum, and it verifies the checksum, and it may or may not use a hash computation to verify the checksum. And this is the pseudocode for the stride algorithm. And a lot of the code involves creating a random number here in the code. It looks like what it does is it finds a random place in memory in the SWORT code to generate the checksum. And in here in the code, they find a random number, a stride number, to step through the addresses and RAM memory in the device. And so as you can see, a lot of this involves random number generation, and fooling the malicious attacker involves hoping that the malicious attacker can't guess these random numbers, and hoping that within 20 milliseconds the checksum can be verified before the malicious attacker can guess these random numbers. Because if the malicious attacker can guess these numbers, then they can calculate the checksum. And one of the differences between this memory stride algorithm and the alternative full memory walk, or I should say the main difference, is that in order to the full memory walk uses the entire memory set to calculate the checksum, as I showed earlier, and the stride algorithm uses only a portion of the memory, so that cuts down on the time to calculate the checksum. This is the algorithmic, the big O time to calculate the time it takes to calculate a checksum for the interleaved memory stride algorithm. And the L is the code covered by the stride algorithm, the amount of memory that is covered by the stride. And S of L is, well, I'm not sure exactly, that they use discrete math to calculate this algorithm. And it involves they use another research paper to benchmark, or I'm sorry, to process how much time it takes to calculate the checksum. And for the full memory walk, this S is just the amount of memory contained in the device. It has to go through every memory word in the device in order to calculate the checksum. And as an example, to illustrate the amount of time saved by using the memory stride algorithm instead of the full memory walk, a device with 16 kilobytes of RAM might use a big O of 16,000 and a one utilizing the memory stride with 1 kilobyte of stride. I calculate that 1000.06, according to the paper, the equation that they use to calculate the amount of time for the big O is 1000.06. So according to the equations that they provide, the memory stride algorithm is 16 times faster than the full stride. And they use these devices in their research. They use actual physical devices to calculate the time it takes to calculate the checksum. And these devices are theoretical. They use the probability and discrete math equations that they came up with to calculate the time to calculate checksum. And as you can see from these two columns, the full RAM walk, most of these, all of these are above 20 milliseconds to calculate. And the memory stride is, all their calculations are below 20 milliseconds. And they, the random, the numbers for stride generated by a nonce, if they calculate that the amount of assurance that a malicious attacker can calculate the random numbers or come up with the random numbers, they call it 10 nines assurance and 5 nines assurance. So there's if it's 10 nines, then there's a 99.999 etc. % probability that a malicious attacker can't guess the amount of stride and the random number, the random word of memory that's the checksum algorithm starts with. And 5 nines, it's 99.999% probability that the malicious attacker can't guess the sums or the checksum numbers. And as you can see, a 10-9 assurance takes up more time to calculate the checksum, but it's still, as compared to the 5 nines assurance, but it's still within the 20 millisecond benchmark to calculate the checksum. Let's see. So the conclusion that I can see in this paper is that the stride algorithm proposed in this paper could potentially provide better security for devices with ARM CPU architectures. In other words, devices on the power grid, if it can be properly implemented and its claims about the chances of guessing the memory map of checksums utilizing its algorithm can be verified. The discrete math and probability calculations are kind of complex that they use to come up with the chances of a malicious attacker to compute the checksums, and the way they calculate big O for the stride algorithm and the full memory walk. So if those can be verified and the SWORT can be implemented effectively in industrial control system devices with ARM processing, I think this This seems like an efficacious implementation and a efficacious paper. And of course, my reference is the paper itself for the material for this summary. And thank you for your time.